Hello and welcome to this video on solubility product. My name is Kim, and in this video we'll be predicting the saturation of a solution using the various clues provided in the question stem and comparing it to the KSP value. I like to think about dissolution and saturation as how willing ions are to be in solution next to each other. Some ions, like sodium and chloride ions, have tiny personal bubbles and are completely fine being super crowded in solution. The sodium chloride KSP is huge, and high concentration of sodium ions and chloride ions are able to exist in solution. Most of the salts you have solubility problems with will have huge personal bubbles, and so you can't fit as many ions in solution. Saturation is a term that will tell you if it's overcrowded, just at the right level, or more can go into solution. In my solution of sparingly soluble salts, you can see that there's still space between the molecules, so this would be an unsaturated solution. I can add more of the same ion and it would still stay in solution. I could even add some solid salt and it would dissolve into solution, since there is still some space. Unsaturated solutions will have a QSP that is less than the KSP. The comparison of QSP and KSP is covered in another video. A saturated solution, as indicated by my beaker completely filled with molecules, cannot fit any more in solution. Adding any more ions will not add into solution, but instead will precipitate out as a solid. Similarly, adding more solid AB will not add into solution. The QSP of a saturated solution will equal the KSP. In an earlier video, we reviewed how KSP can be increased or decreased by changing the temperature for solid dissolution and changing the temperature and pressure for gas dissolutions. The creation of a supersaturated solution is taking advantage of this principle. By increasing the KSP, by manipulating pressure or temperature, we can cause more ions to go into solution. Then, by slowly changing the condition back to what was originally there, we'll cause more of those solids to stay in solution than would normally occur. Both of these solutions are at the same temperature, as indicated by my cartoon thermometer. However, the solution on the right has way more ions in solution compared to what it would normally hold at that same temperature, so it is supersaturated. A supersaturated solution will have a QSP that is greater than the KSP. The applied questions ask for a prediction of the saturation of the final solution in each part. In A, 40 grams of silver sulfate is added to 1 liter of water at room temperature. It's noted that not all of the silver sulfate is dissolved. Now, this question seems to indicate that math is necessary, and we could, but since the question is just asking for the saturation level and nothing else, let's use the clues in the question stem. Since only some, but not all of the silver sulfate dissolves, the maximum number of ions have gone into solution. That means the solution itself is saturated. No more ions can fit. Part B is a large multi-step problem, so let's analyze what's going on in each step. 1 gram of lithium carbonate is mixed with 100 milliliters of water. However, not all of it is in solution. At this point, just like in part A, the solution is saturated. Then the solution is heated, and while the enthalpy isn't explicitly stated, you can assume that it's endothermic, since heating the solution causes the solid lithium carbonate to dissolve. That means we've increased the KSP of lithium carbonate. Finally, decrease the temperature will also decrease the KSP, but since all of it stays in solution, it must mean that the final solution has more ions than is normally supported by the KSP, and the solution is supersaturated. Make sure you review the elements in this video and earlier videos in this series to help you make predictions on saturation in your practice.